Hi, welcome back to EAW. If you watched our video on beam width matched crossovers, then you may recall me saying something about the anomaly in the vertical polar measurement we made of the two-way loudspeaker. Well, today I'd like to dig a little deeper and explain two more EAW core technologies, the symmetry of sources and space low frequency. To understand these technologies, we'll have to talk some about the fundamental physics of sound. But don't worry, it's not as difficult as it sounds, so to speak. We'll start with the point source. Now, you may ask, what is a point source?
Yeah, what is a point source?
Thank you, I'm glad you asked. Well, a point source is an infinitely small source that radiates energy in all directions with equal level and phase at the same time. Well, of course, that won't work in audio because all of our transducers have some kind of size. But as long as the wavelength is significantly greater than the size of the source itself, then the principles still apply. So let's assume this little styrofoam ball is an acoustic source. Now it generates a sound, and that sound radiates spherically in all directions, kind of like a balloon. So let's assume our source is in the middle of this balloon. Now what happens if I take a second source playing the exact same material and I put it at some half wavelength of space away from my first source? The resulting balloon would end up looking something like this. We have nulls above and below, but we have addition on axis. So let's take a measurement or two and let's see how this works. As you could see in the measurement video, this source is a single 5 1/4 transducer in a 6-inch enclosure. The wavelength of 6 inches is about 2K, so frequencies with wavelengths greater than 1 foot will behave mostly like a point source, and we see that down at frequencies below 1000 Hertz or so. But where wavelength approaches 6 inches, up here around 2K, we see this loudspeaker become increasingly directional. Now let's do the measurement again with two sources about 6 inches apart playing the same signal. Now we clearly see some collapse in polar pattern here around 800 Hertz and up. The wavelength of 1K is about 1 foot, and these sources are spaced 6 inches apart, about a half wavelength of 1K. So we get cancellation like the balloon I showed you earlier. Now this is what makes audio really interesting and a little bit magical. This interaction of multiple sources can give us some very desirable characteristics in a loudspeaker, but at the same time they can cause some real problems for the designer who doesn't manage the physics appropriately. Now take a two-way or three-way loudspeaker for instance. Now you may say, what does it matter? You have lows, mids, and highs all playing a different range of frequencies. Well, because right at the crossover point you have two sources playing the same material through a small range of frequencies, and they are vertically offset in this box. So we get that vertical collapse of pattern that we saw in our last measurement. But we also have an offset from front to back. The acoustic origin for the low frequency is somewhere up in this area, while the high frequency origin is a little farther back in the cabinet. So it causes that lobe and the nulls to actually steer up. Now let's take another look at that measurement we made in the beam width match crossover video and see what we can find out. The first thing we see are these holes in the polar pattern at the crossover point here and here. Second, we see the different arrival time of the lows about here and the highs around here. Now we can improve this somewhat on axis by putting a little delay on the lows, but it would only fix the problem for that one point in space. It doesn't fix it everywhere, and this problem is compounded in three-way loudspeakers with separate lows and separate horns for mids and highs. So what can a loudspeaker designer do to fix this problem? Well, some manufacturers try to use steeper crossover slopes, but that doesn't fix the problem. It just makes the range of affected frequencies a little bit smaller. And those steeper slopes add huge amounts of phase shift, so you're just creating more problems somewhere else. If you ask the geniuses in our engineering department, they'll tell you the best way to fix this is to symmetrically arrange all of your sources along a single axis front to back, and then just use a little delay to align the arrival of each source at the listener. Voila! No more lobes, no more nulls. Now this is one of the great things in our microwedge series of floor monitors. We use a coaxial transducer instead of side-by-side low and high-frequency horn. So let's take a measurement of the MW8 and let's see how that looks. Let me remind you that these flares we see here are just due to the measurement environment and some bumps in EQ. I should also point out that this is a passive loudspeaker, so we do have a little offset in the arrivals of the lows here and the highs here, but they are much closer together because we are using a coax driver, which minimizes any dip in the response at the crossover point. Of course, this is easily fixed when we bi-amp the loudspeaker and add a touch of delay to the lows. More importantly, though, is that we've eliminated the steered lobe around the crossover point. And if you listen during the measurement, you don't hear nearly as much sweeping as the loudspeaker rotated as you did with the typical two-way. Of course, this measurement would be the same both vertically and horizontally because highs and lows are arrayed along a single front-to-back axis. That's pretty cool, don't you think? Well, earlier I mentioned that we could use this interaction of multiple sources to give us some very useful results. Earlier I made this measurement of the two sources side by side. Well, they were spaced about 6 inches apart, which is a half wavelength of about 1,000 hertz. What we saw at very low frequency was that the pattern of the two was basically omnidirectional. This is because the wavelengths of those frequencies is much greater than the spacing of the two sources, so they just sum together. Then around 500 hertz, we saw that pattern start to collapse, and as we got higher in frequency, the pattern got more and more narrow. Now we can use this phenomenon to give us extended pattern control down to very low frequency. This is another EAW core technology, spaced low-frequency sources. Now let's do this measurement again. This time I'm going to space them about a foot apart, which is a half wavelength of 500 hertz. And let's see what happens. Now that pattern collapse is happening way down to about 350 hertz. We also get these additional lobes up here around 700 hertz, which we probably don't want. So we would apply a low-pass filter to eliminate these problem lobes. Compare this to the measurement of the sources at 6-inch spacing, and you see how we simply change the spacing of the sources to achieve pattern control at the range of frequencies we want. So think about this. If we were to try to control this range of low frequency using a horn, we'd have to build a horn somewhere around 4 feet to 5 feet in size. As you can see, we can accomplish this much easier simply by applying the laws of physics, by using spaced low frequency sources to give us that pattern control. Now this is the KF394, and you see right away our spaced low-frequency sources. We get useful vertical pattern control all the way down to about 300 Hertz. This also is a three-way loudspeaker. We've actually combined mids and highs on a single horn. Now we'll talk more about that in another video, but the point is that highs, mids, and lows have all been symmetrically arrayed around a single axis front to back. We just add a bit of delay to align the arrivals at the listener, and we've eliminated the lobes and the nulls. Also note that this has a very large horn, and we've applied beam width match crossover technology to this loudspeaker as well. You put all of that together, you get an amazing product with remarkable pattern control in a remarkably small package. And we've taken our technology to the next level in our premier installation loudspeaker, the QX. Here we have a very large mid-high horn and four 12-inch transducers in a vertical pair and a horizontal pair. So we give you unprecedented vertical and horizontal pattern control, and no other manufacturer has a product that can compete with this. In fact, if we look at the polar plots for the QX, we see that at 90 degrees off axis, we give you 10 dB of attenuation down at 160 Hertz. This is a critical requirement for highly reverberant spaces such as nightclubs, performing arts venues, indoor arenas, and stadiums, and it explains why QX has been dominating the install world over the last year or so. And we haven't even talked about focusing technology yet, but that's a topic for yet another video. Now I hope you're starting to see a pattern here, a pattern of how EAW engineering doesn't fight the laws of physics, but they apply the laws of physics in innovative ways that give us amazing products. Now you can find these core technologies of space low frequency and symmetry of sources in a lot of our series, starting with the SMS series. And it's pretty easy to spot because you'll always find the high or mid-high in the middle, and then the low frequency spaced symmetrically around it. You'll also find it in the AX series, the QX series, and the KF series. Now if you'd like more information on the fundamental physics of these technologies or other EAW core technologies, then be sure to check out the support section of our website. I'll see you in the next video, but until then, I wish you lobe-free, consistent beam width. If you saw our first video on beam width match crossovers, then you well, it's cold. And I can't get this thing tight. My finger's stuck. How do I do this? My source is dirty. You dirty source.